Hey folks, we are going to continue with projectiles today. This is actually our last lesson of the chapter. We've made it to the end of chapter 4, which is kind of cool. What we're going to do with the projectiles today is we're going to look at projectiles that are maybe more common. We're going to call this angled projectiles. So instead of an object only doing like a half parabola shape, sort of rolling off of a cliff or a building, we are going to look at, like this example, somebody kicking a soccer ball, could be throwing a baseball, shooting a basketball, something like that. So here we can see we've got a soccer player kicking the ball with an initial velocity of 24.5 meters per second. But that initial velocity is at an angle of 30 degrees. We're asked to find the range of the ball. Remember, range in physics just means the horizontal distance that the object is going to travel. So if you wanted to put it in your diagram, that's what the range is. And remember, with all projectiles, we don't think about the horizontal and the vertical together. We think about those two movements being totally separate. So this 24.5 meters per second of initial velocity, because it's at 30 degrees, we're going to have to fix that a little bit. That number, in fact, is not going to work for us. So what we'll have to do is we'll have to figure out, of the 24.5 meters per second at 30 degrees, how much of that is vertical and how much of that is horizontal. So the first step with this kind of question is we actually have to resolve that initial velocity. We have to break it down into its components. How much of it is vertical, how much of it is horizontal, and then it actually becomes a lot like a regular projectile question, like the kind we saw in the last video. So I'm going to draw on this initial velocity as a 24.5 meter per second vector. And I know this thing is at 30 degrees compared to the ground. And we want to figure out how much of that is vertical and how much of that is horizontal. And what's cool is this is a right angle triangle, so we can go with some nice easy right angle trig, SOHCAHTOA. So the sine of 30 is equal to opposite over hypotenuse, and the cos of 30 is equal to adjacent, h over hypotenuse. And that'll really quickly let us solve for v and h. We're simply going to multiply 24.5 and the sine 30, multiply 24.5 and cos 30. So 24.5 times sine 30. Sine 30 is actually worth 0.5. So that's going to come out as a nice number, 12.25 meters per second. Oops. So that's going to be the initial velocity vertically. And the horizontal initial velocity, if you remember from special triangles, what's cos 30 is like root 3 over 2. I'll need a calculator for that. 21.218. 21.218 meters per second. So there is the vertical velocity and the horizontal velocity, the initial velocities anyways, that are going to go into our two-column VFDAT table. So now we're back into the kinematics. For a moment, this is going to look quite similar to what we saw in the last video. Remember that there's a few numbers that we can always put in there. We know that vertically acceleration is negative 9.8. Horizontally, there is no acceleration. Once this ball is flying through the air, there's nothing to speed it up or slow it down. That means VI and VF will be the same value, and time is the same. So what we're going to do, a little bit of a change here, is that 12.25 meters per second that we saw for V means vertical, that's actually the vertical initial velocity. The last few examples in the last video, the initial velocity in the vertical direction was 0, but this time we have some VI. So that goes in as 12.25. Horizontally, there's nothing to change the velocity, so I know I called it hi for the initial velocity, but it turns out it's actually both velocities. 21.218. There's one other value that we sort of know in this question, and you have to go back to maybe the picture to see it. I want you to think about what this ball does just in the vertical direction. The ball starts on the ground right here, and it travels up to some maximum height, and then the ball falls back down to the ground and lands on the pitch. Lands right there. So I could ask you vertically, don't worry about horizontally, but vertically, what's its displacement? Well, if it started on the ground and it finished on the ground, then the vertical displacement is actually 0. So I'm going to put that value in there. The overall question mark is the horizontal distance. Hey, look at that. We're going to scratch the vertical VF just like we did in the last 3 examples in the last video. And that means vertically, we're back to the same equation as we have always used. So we're going to start with some vertical information. We're back to d equals VIT plus 1/2 AT squared. And some of you at this point might be looking at those values that need to be plugged into that equation, and you might be going, uh-oh, this looks like it could be a quad formula question. Because in the last example, or examples, we crossed out this VIT. It didn't exist because the initial velocity was 0. But in this case, we do actually have some initial velocity, so we actually can't cross that out. So 0 equals 12.25 t plus 1/2 times -9.8 times t squared. It turns out that this can be quadratic or not, which is kind of cool, and I'll show you what it looks like if you don't want it to be quadratic. I'm simply going to combine the 1/2 and the -9.8 here. That becomes -4.9 t squared. If you want, you could totally run this as a quad formula question, where you would have -4.9 as A, 12.25 as B, and you actually don't have a C value. The 0 would be your C. So if you've got quad formula on your graphing calculator, that's a great option. But there is another option here, which is kind of cool. And that option, don't write this part down, but that option is like when you factored trinomials in math class. And maybe some of you are groaning about that. When you factored trinomials, you might have ended up with a factoring that looks like this. So don't write this down. But if this was x plus 2 times x minus 3 equals 0, I could say, what are the answers for x? And you would look and say, oh, it's easy. X equals -2, x equals +3. And the way you get that is you take each bracket and you set it equal to 0. So in order to solve for the -2 and the -3, sometimes students forget how that actually even happened. Was you took this first bracket and said, what could I make x to have that bracket equal 0? And we did the same thing on the x minus 3. What could we plug in for x to make that bracket equal 0? And that's where we got the -2 and the +3. Well, it turns out we can actually factor this equation that we've got for our angled projectile in much the same way. Don't overthink this, but I would say, what could you really easily factor out of the 12.25 t and a -4.9 t squared? Well, you could factor out a t. So if we do that, if we factor out a t, there's one bracket. That leaves us with 12.25 with no t attached anymore, minus 4.9 with just a single t attached. Now what we're going to do is much like what I did in that factoring I said not to write down. We're going to take each of these brackets and we're going to set them equal to 0. So the first one, done. Super easy. T equals 0. On the second set of brackets, it's 12.25 minus 4.9 t equals 0. To solve for t on that one, I would probably add 4.9 t to both sides, make it positive. So now we're into some nice easy algebra. Equals 4.9 t. Divide both sides by 4.9. T equals, get that out of the way, 2.5. And that would be s for seconds. Now the question becomes, which of those times is the one that we're after? Or maybe the other question is, why did you get two answers? Right? Why do we have two time values? And what we just asked the math to do was we just asked the math to tell us at what times is the ball at a displacement of 0. So we asked the math to tell us, when is the ball touching the ground? Displacement 0. Well, if I go back to my picture, the ball is touching the ground before we kick it at time equals 0 seconds. And then the math said, hey, it's actually not touching the ground again. It's airborne for 2.5 seconds. And that's when it touches down onto the field again. So that's going to be the value that we're after. But that is why you get two values. You get the 0 seconds and the 2.5 seconds. So we now know that this ball was airborne for 2.5 seconds. And that means we can move into our usual horizontal equation. I'm going to squeeze this in here if that's okay. Horizontally, we're back to good old d equals v times t because there's no acceleration. We're looking for the horizontal d. I have to go back up here. What was the horizontal velocity was 21.218. 218. We know that ball is in the air for 2.5 seconds. The range of this ball is 21.218 times 2.5. Looks like 53.0 meters. Quite a good boot, a good kick. There we go. Final answer. So that's your angled projectile question. A little bit more going on there, right? Because we had to start with resolving the initial velocity. That was an extra step. And then running the vertical equation was a little bit different. Again, you're welcome to run it on your graphing calculator as a quad formula. But I like to call these gently quadratic because you can actually just factor out a t and solve that way. In fact, for those of you with calculators, let's try this really quickly. I think I have quad on here. Just to show you that it would work on your calculator, we had said a could be negative 4.9, b was 12.25, c is 0. There's your 0 and your 2.5. So you've got a couple of different options. If you don't have quad formula on your graphing calculator, you just have to go through this factoring method. Takes you an extra few seconds, but not a big deal. There's chapter 4. That's a wrap. Kind of cool. We're done. The homework that goes with this is, let me bring it up here, back to worksheet 1. I just want you to try numbers 19 and 20. It's basically the same question where I switch up the angle and the velocity a little bit. Part A says determine the initial components of the velocity in the x and y direction. That just means resolve that initial velocity into its vertical and horizontal components. You can skip the maximum height if you want. It's totally fine. I'm not going to ask you to do that. What I do want you to know, though, is how to find the range of the arrow. How far did it move horizontally? So try 19 and 20. Those are the questions to give a go. Again, there's a little bit more going on, but make sure you try this out. Make sure if you have any questions, you either get in touch with me via email or join me in one of the Zoom group chats. So I hope to see you soon. There will be some assessment now that we're at the end of this chapter. We're going to do a sort of take-home, while you're at home, a take-home quiz / assignment that you hand in and I actually mark. I'll give you more detail about that coming up. The other document you can try that's on the website is the Chapter 3-4 Extra Help. It's in that all resources folder. Give that a go too once you've got these angled projectiles figured out. And we'll be in touch soon about what that assessment, test, assignment piece will look like. Yeah, I'll give you more detail upcoming very quickly. Any questions? Get in touch. Take care.